Hi everyone, welcome to Organic One. We're going to start chapter 1, Structure and Bonding. In this video, as a reference to this chapter, you can use John McMurray 9th edition. This is the organic book that we will be using. Chapters 1 and 2, they summarize a chapter 1 in this PowerPoint. Normally these PowerPoints are kind of like comprehensive. So in case you would need additional information, you can go ahead and read more in the chapter. It's not a must to read more because I normally include everything in the chapter. Now, in order to access the book, you would need to buy an electronic access. And this electronic access is for Organic 1, Organic 2, Lab 1 and Lab 2, and the package costs like this, and you can easily log into Cengage.com unlimited/unlimited in there. Here you go, and you can subscribe and get the access to that. Now, why do we need the access? We simply need the access because through this access you will have an electronic copy of the book. This is the first thing. You will have an electronic copy of the solution manual for the book. Normally the book will have some problems in there, and these problems will have a solution to them. So in order for you to view the solution, you would need the solution manual. Also, the package will have access to the Organic Lab book. For both Lab 1 and Lab 2. Now, this package over there, we're gonna use it for assignments, and we're gonna use it for quizzes. So this is why it's a must to get it. On top of this, we would need a Top Hat subscription. This is for exams and for extra assignments. Sometimes not all of the topics are covered in the Cengage Unlimited. So we would need additional assignments, and those additional assignments you're gonna find them at Top Hat. It's www.tophat.com. You can access there and you can buy the subscription. The subscription is $30, and it's gonna cover you for both Summer 1 and Summer 2. So these are the fees that you're gonna basically spend on Summer 1 and Summer 2 together. You're not gonna spend more than that, except if you are taking the lab, then I would let you buy an additional $25, which is beyond labs. It is a special type of platform for the lab. You would also need for the course, this is recommended and it's not a must, but I would really recommend that you would get this because you would need it for chapters 4 and 5. The molecular model set, this is highly recommended. All what you need to do, let me show you. You don't have to go to Amazon, just type molecular model set, but this is what I want. This is like the best. This is the best in there. The stick model is not convenient, so the ball and the stick model is the best. You can find it cheaper than $21.95. If you find it, then go ahead and get it. Just make sure that you have this, and we would need it for both the chapters 4 and chapter 5. Normally every week we will be covering 3 chapters per week. So when we get to chapter 4, that will be the second week of the classes in there. Okay, so pretty much this is everything that we need for Organic 1. So let's start the chapter Organic. What is organic? Organic is the chemistry or the study of carbons, how carbons are bonded together, and how carbons are bonded to hydrogens. So carbons can make bonds with each other, as you can see over here, a carbon single bond carbon, and carbons can make bonds to hydrogens. Carbons can make bonds with each other, making single bonds, they make double bonds, and they make triple bonds. When carbons make single bonds, the structure will be called alkanes, and as you can see, we are connecting the carbon chain together. Carbon follows the octet rule. Octet rule is simply for elements in the second row of the periodic table. This is the elements in the second row of the periodic table. Okay, let me take those out. Elements in the second row of periodic table including, okay, carbon, nitrogen, oxygen, and the fluorine. These elements in the second row of the periodic table, they follow the octet rule. What is the octet rule? Octet rule is basically saying that each of these elements should have 8 electrons. They should have 8 electrons in their outermost shell. Whether between owning electrons and sharing electrons, they should have 8 electrons in their outermost shell. Also, chlorine, bromine, and iodine, they also follow the octet rule. So they should have 8 electrons in their outermost shell. This means that they should share 8 electrons. When you draw a structure, a hydrocarbon structure is a structure that is made up of carbons and hydrogens. We call it a hydrocarbon structure. Make sure that the carbons are always connected with each other. They're always connected with each other. And carbon always makes or forms 4 bonds. So carbon should always form 4 bonds to the neighboring atoms. So if carbon forms 4 bonds, and I am looking at the alkene structure here, alkene means a double bond. So look at this carbon. Carbon is forming 1, 2, 3, and 4. Carbon is forming 4 bonds here. This carbon is also forming 4 bonds. This carbon here is forming 4 bonds, so it's going to be 1, 2, 3, and 4. So 4 bonds on this carbon and 4 bonds on this carbon. These are the 3 different types of hydrocarbons that basically carbon hydrogen make. They can make carbon single bond carbons, they can make carbon double bond carbons, which we call alkenes, or they can make carbon triple bond carbons, which we call alkynes. The point is, carbons always, they follow the octet rule. This means that they should always share 8 electrons. They own 4 electrons and then they share 8 electrons. In this chapter, we're gonna review 115, just the material that we need. Just the material that we need from Gen Chem 1. The first thing that we need is Lewis structures, how we draw a Lewis structure. For example, if I give you the inorganic compound hydrogen fluoride and I ask you just go ahead and draw its Lewis structure. Drawing the Lewis structure means representing the molecule, just showing how the electrons in the molecule are represented or they are distributed in the structure. So Lewis structure is basically a drawing of how electrons are present in the structure. So at the end, your structure should show the electrons that are present in the whole compound. So the first thing that you would need to do, you would need to find the valence electrons. This is the first thing that you would need to do. Now, what is the valence electrons? Valence electrons, these are electrons in the outermost shell. And they basically correspond to the group number. So if you're looking at the group number 1, the valence electrons are 1. Hydrogen has 1 electron in its outermost shell. Group number 2, valence electrons is 2. So valence electrons is equal to the group number. This is equal to the group number. Group number 3 has a valence electrons of 3. This means that it has 3 electrons in its outermost shell. Group number 4 has a valence electrons of 4. Group number 5 has a valence electrons of 5. Group number 6 has a valence electrons of 6. So the point is that valence electrons is equal to the group number, okay? And the group 7 has valence electrons is equal to 7. Now group 8 is inert. Group 8 is inert. So the number of valence electrons in a group 8 is 0. This is 0. This is the number of valence electrons in there. There are no electrons in the outermost shell. So let's go ahead and calculate the valence electrons just to show you how. The valence electrons, as we said, it is the group number. So hydrogen is in a group 1, so it has 1 as a valence electron. Plus fluorine is in a group 7, so it has 7 valence electrons. 1 plus 7, this is an 8 valence electrons total. There are two ways to draw the Lewis structure. One, it's called the electron dot structure, and the other one is called the bond or the line bond structure. I'm going to be using the line bond structure, but I'd like to explain both, and then we will be carrying on with the line bond structure for all our problems. So in order to draw the electron dot structure, all what you need to do is just show the hydrogen with 1 valence electron. This is a group 1. Fluorine with 7 valence electrons. Count them. These are 7. And then remember that every bond is the overlap of 2 electrons. So when 2 electrons basically overlap or combine, you make a bond. So see these 2 electrons in here? These 2 electrons, they're making a bond. That bond, you can either represent it as 2 electrons or you can represent it as a line. Representing it as a line is easier, and this is what we will be using. And the structure, we're going to call it line bond structure. It's still a Lewis structure. When you draw any Lewis structure, you want to make sure that electrons are present, and you should distribute all the electrons. So see now, I calculated the number of electrons to be 8 valence electrons. I have to distribute that, count it. This is 1, 2, 3, 4, 5, 6, 7, 8. So I do have 8 electrons, 8 valence electrons that are shared between the hydrogen and the fluorine. Hydrogen has 1 electron, and it's sharing 1 electron with the fluorine. Fluorine has 7 electrons, and it's sharing basically 1 electron, sharing basically 2 electrons in there. So it's sharing 2 electrons with the hydrogen. So again, hydrogen has 1 electron, and it's sharing 2 electrons, because when you add the sharing electrons, you should basically count the 2 electrons in the sigma bond. So I'm having 2 electrons in here in the sigma bond. I'm forming an H and an F. So hydrogen has 1 electron, and it's sharing another electron with the fluorine. Fluorine has, because it is basically in a group 7, so it has 7 electrons, okay, it owns 7 electrons, and it's sharing 2 electrons with the hydrogen. So the sharing, you count the 2 electrons of the sigma bond in there. Now, sometimes if the valence electrons, they are all used. So if you use, for example, if all the valence electrons are used and still the atom does not have an octet, like for example here, I'm having an example of C2H4, okay? Now the valence electrons for C2H4, this is going to be equal 2 times 4, this is going to be equal 8, plus 4, so the valence electrons are going to be 12. The way you draw it, you draw a carbon, single bond carbon, you always connect the carbons together. Then the hydrogens over here, you're going to divide them over the carbons. Because you have 2 carbons, each carbon is going to take 2 hydrogens. So you have a hydrogen here, and the hydrogen there, and the hydrogen here, and the hydrogen there. I am using the bond line structure. This is what I am using. I'll show you the electron dot after I finish this. So this is the bond structure in there. So right now, see how much I used. You count the sigma bonds, you count the bonds in there. I used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Every single bond is 2 electrons. So I used 10 electrons. How many I still have? 12, right? So I have 2 more. Basically, from 12, I have 2 more. So you have 1 here and you have 1 there. Now, here's the thing. The structure having 1 electron on the carbon like that is completely unstable. So what you're going to do over here is basically combine these 2 electrons and make them a bond. You make them basically a single bond. So you take the eraser and you erase this electron and make a bond in there. So you will have a double bond between the 2 carbons. So see what I did over here. These 2 electrons instead of having them one carbon on one electron on one carbon, one electron on the other, in this structure we're putting them both on one carbon. And then since you're putting them both on one carbon, you're going to end up having this carbon not being octet, which is completely unstable. You want to make sure that each of these carbons is octet, having 8 electrons. And to do this, you would need to share the lone pair, not just make the lone pair being owned by this carbon. You have to also share it with the other one, so you have to make a double bond. This is one way of drawing the Lewis structure using the line bond structure. You could have drawn the Lewis structure using the electron dot structure like this, where I'm going to use that same example. So I know that carbon has 4 basically valence electrons. So you draw the 4 valence electrons like this. And the other carbon has the 4 valence electrons. So you just draw it like that. Okay. So now we're gonna have the hydrogens. Each of these hydrogens have 1 valence electron. So I have a hydrogen here, and then I have a hydrogen here with 1 valence electron, and a hydrogen here with 1 valence electron. So all what you can do over here is just combine 2 electrons to make a bond. So every 2 electrons make a bond. So you can make a bond here. Combine these 2 electrons, you can make a bond there. Combine these 2 electrons, make a bond here and make a bond there. And these 2 electrons, just combine them and make a bond. So you will be left with an electron on the carbon and an electron on the carbon, same as this this case that we explained earlier. So all what you need to do is just go ahead and take these electrons and simply draw a double bond. Simply draw a double bond between the 2 carbons. This way, each of these carbons is going to be octet. When looking at a carbon having 4 bonds, what does that mean? A carbon having 4 bonds means that carbon owns 4 electrons. Carbon is going to always own 4 electrons to be stable and to be 0 formal charge. Because carbon is in a group 4, it has 4 valence electrons. So here, when carbon forms 4 bonds, it owns 4 electrons. These are the 4 valence electrons. And carbon, it shares actually 8 electrons. So it shares an electron here with, let's say, for example, a hydrogen. It shares an electron here. It shares an electron here, and it shares an electron here. But when I count the shared electrons, I have to count the shared electrons with the bond. So each bond is 2 electrons. So carbon here is sharing 1, 2, 3, 4, 5, 6, and 7, 8 electrons. In this case, carbon owns, see how much carbon owns? 1, 2, 3, and the lone pair. See this? This is called a lone pair. Carbon owns the lone pair. Now the lone pair belongs to the carbon. It's not shared with any of those groups. It's just on the carbon. So I should not count it when I'm counting the shared electrons. So carbon owns 1, 2, 3, 4, 5 electrons, and it shares, see how much it shares over here? It shares 1, 2, 3, 4, 5, 6 electrons. It shares only 6 electrons. Here, carbon owns 1, 2, 3, and 4. So carbon owns 4 electrons. This carbon owns 4 electrons. And this carbon owns another 4 electrons. This is an electron and this is an electron. Now with respect to the sharing, this carbon over here shares, I'm just going to highlight the carbons that it shares. It shares this carbon here, or it shares basically this electron. So it shares 1, 2, 3, 4, 5, 6, 7, 8. It shares 8 electrons. See what I did when I counted the sharing of this carbon, the sharing electrons? You have to count both electrons in the double bond. And the double bond has 4 electrons because each pair of electrons is a bond. Okay, so so each one is a bond over here. So this carbon is going to be 8 electrons, and this carbon over here is also going to be 8 electrons. So both are going to be 8 electrons. Okay, So these are examples for representation of Lewis structure in there. And as I said, there are different ways to represent Lewis structure. There is the electron dot structure, and there is the line bond structure. And we are going to use basically both or just one of them. Now it's up to you to use whatever you want, but I'm gonna go ahead and use the line bond structure in there. I'm gonna show you more examples on how to I'm going to show you more examples on how to use the electron dot structure, but we're going to use the line bond structure as I mentioned because it's actually easier. So for the CH4 again, so the question here, just to draw the Lewis structure, we did already CH4, let's do the NH3. So the question here, draw the Lewis structure of NH3 using the electron dot structure. First thing that you would need to do, as we mentioned, get the valence electrons. The valence electrons here, nitrogen is 5, hydrogen is 1. You have 3 of the hydrogens, so the valence electrons is 8 valence electrons. Now we're going to start drawing it. So to draw it, you put the unique element in the center. And normally, if you have more than one unique element, your low electronegative element goes in the center. Just to remind you that electronegativity increases from left to right in a period, from bottom to top in a group. So, so if you have nitrogen and oxygen, nitrogen is going to be in the center. Hydrogen can never be in the center, even though if it was a unique element, it can never be in the center. Always hydrogens are on the edges. So here I have my nitrogen in there. I want to distribute those 8 electrons. So let's start. Nitrogen has 5 valence electrons. So we're going to draw the 5 valence electrons. I'm going to have 1, 2, 3, 4, and 5. So these are the 5 valence electrons. And then we're connecting the nitrogen to the hydrogen. So I'm going to have a hydrogen here. Each of the hydrogens is going to have 1 electron. Here you go. So this is basically the Lewis structure. So these two, instead of drawing it like this, normally you draw them above each other. So these electrons, again, you draw them above each other. It's like it's an electron dot structure where you do not show any lines or any bonds in there, but just remember that every 2 electrons form a bond. Now what about these electrons in here? There are 2 lone pairs. These lone pairs, what are those? These are basically owned by the nitrogen. So these lone pairs in there, they are owned by the nitrogen. They are not shared. They are owned by the nitrogen. They are not shared by the hydrogens. We call them lone pairs. You do the same thing for water, for this structure. Now for this structure over here, it does have an OH. OH is a functional group for an alcohol. We will talk about functional groups. There are a lot of functional groups, and this is a chapter 3. We will talk about all of these functional groups, but throughout the lecture, I will say the names of these functional groups just to let you be familiar with all of these functional groups in there. Let's go ahead and do the line bond structure. Now for the line bond structure, I'm going to do the same example in there. So instead of showing the 2 electrons, you put the nitrogen as a center atom. And then I know that nitrogen is connected to 3 hydrogens. So this is 1, 2, and 3. So see, now I'm drawing bonds. And there you put the hydrogens and then you start counting. You start counting. I need 8 electrons. So far I've used 1, 2, 3, 4, 5, 6. Any left over, I have 2 electrons left over, you just go ahead and put them on the nitrogen. Okay? Let's go ahead and do this example over here. This example is a CH3OH. This is the molecular formula of methanol, CH3OH. This is a molecular formula in there showing carbons, hydrogens, oxygen, and hydrogen. Now when I draw OH like this, see this hydrogen, I did not combine it with this hydrogen and said CH4O. I said CH3OH. So this means that the oxygen is connected to the hydrogen. First of all, get the valence electrons. So the valence electrons here is going to be 4 plus 3 plus 6 plus 1. So this is 10, this is going to be 14. Valence electrons is always even. It is not odd. So once you find the valence electrons, just go ahead and put the low electronegative unique element in the center. How many unique elements we have? We have carbon, we have oxygen. The lower electronegative one is the carbon, so you go ahead and you put it in the center in there. Now around the carbon, what do I have? Around the carbon I have 3 hydrogens, so you go ahead and you put the 3 hydrogens. Here you go, you put the 3 hydrogens, and then connected to the carbon I have an oxygen. I already did the 3 hydrogens, so connected to the carbon I have an oxygen in there, and then next to the oxygen I do have a hydrogen. See, I just follow the trend of the molecular formula. There is no way that I'm going to have a carbon, hydrogen, and then an oxygen like this. A hydrogen can never exist between 2 elements. This is not right, because normally hydrogen has only 1 valence electron, and in this case it's having 2 valence electrons. So this is not right, and it cannot be acceptable. Always hydrogens, they are on the edges, okay, because they should only have 1 valence electron. So all of these hydrogens have 1 valence electron in there. Now after I do this, you go ahead and you count your electrons. How much did you use? I used 1, 2. Each sigma bond is 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many I have left? I have 14 left. So these 14 left, they go on the oxygen. They don't go on the carbon. Why? Because the carbon already is octet, already is making 4 bonds. You cannot put more electrons on the carbon. So the leftover are going to be put on the oxygen. Remember what we said at the beginning. Oxygen follows the octet rule. So oxygen should have 8 electrons, and this is what I have. 1, 2, 3, 4, 5, 6, 7, 8. So oxygen now has 8 electrons, carbon has 8 electrons, so my structure, this is going to be my Lewis structure. Notice when you represent the Lewis structure as a bond line, you should show the bonds to the carbons and hydrogens, and you should show the lone pairs on the electronegative atom. Let's have another example, which is the aldehyde. Okay, aldehyde is basically a carbon double bond O connected to a hydrogen. This is another type of functional group other than the alcohol. It can exist where carbons make double bonds with oxygens. So let's have a space over here to draw this example. Okay, so the first thing that you're going to do is calculate the valence electrons of the aldehyde. So to get the valence electrons of the aldehyde, you would need the molecular formula though. So transfer this into the molecular formula. So it's going to be CH2O. Okay, so this is going to be CH2O. See how I drew it? It's a CH2O. The hydrogens, they are on the carbon. The valence electron in this case is going to be equal to 1, 2, 3, 4, 6, 7, 8, 9. Okay, so it's going to be 12 valence electrons. You have 4 electrons, you have 2 electrons in here, and then 6, so it's going to be 12 valence electrons. You start by putting the low electronegative element in the center. This carbon is connected to 2 hydrogens, just to draw lines to the hydrogens. So far how much I used? I used 4 electrons, 1, 2, 3, 4 out of 12. I still have 8 more. Okay, and then I'm having an oxygen in here. See that oxygen? This is my oxygen in there. After you do this, we're going to go ahead and fill out any leftover electrons from the 12. So I used 6 so far. 1, 2, 3, 4, 5, 6. I still have 6 more. So to fill out the 6 more, don't fill the carbon. Not now. Leave the carbon, the central atom, till the end. So this is going to be 1, 2, 3, 4, 5, 6. I am done with my 12 valence electrons. I am done with those. But I have oxygen octet, yes, but see the carbon? The carbon has 6 electrons actually. So the carbon is not octet. This is an easy fix. When you have this case, always, this is what you do. Take electrons, 2 electrons from the oxygen. I know every 2 electrons make a bond. So you can make a double bond with the carbon. So you can make a carbon double bond oxygen in that case. Another example, draw the Lewis structure of carbonic acid. Carbonic acid is an inorganic acid, so get the valence electrons is 24. And then go ahead and put the unique element in the center. Okay, so we're putting the unique element in the center. Here you go. And then connect the unique element to the oxygens because it says so. It's CO3. So the unique element has oxygens around it. Now, what about these hydrogens? Are they on the carbon? No, they are not on the carbon. How would you know? Whenever you have carbons and oxygens, leave the carbon alone. Don't put hydrogen on that. Reason why? Because you can't fill any extra electrons that you want to add for the octet. You can fill them by simply making a double bond with the carbon and the oxygen. But we want to make sure that these hydrogens basically are on the oxygen so that oxygen follows the octet rule. So each of these hydrogens can be on the oxygen. You can choose any oxygen you want from those three and stick a hydrogen to it. So far I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Continue to the 24, 11, 12. See, I started with the oxygen. I didn't start with the carbon. 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, and 24, and I am done. I am done. Everything is good except what? Except basically the carbon. The carbon is not octet. The carbon has 6 electrons. So this is an easy fix. All what you need to do is simply take the lone pair from the oxygen. And which oxygen am I targeting? I'm targeting the oxygen with this single bond, with a 1 bond in there. So you take the lone pairs from this oxygen and you simply make a double bond. I did not take the lone pairs of this oxygen here because if you did, you're going to make a double bond here. If you made a double bond in here, oxygen will have 3 bonds. It will have a charge of +1. We will talk about formal charges as we proceed. But by doing it this way, oxygen has a 0 charge. Oxygen here has a 0 charge because it has 2 bonds and 2 lone pairs. And oxygen here has also 2 bonds and 2 lone pairs. It has a 0 charge. So the whole charge of the carbonic acid is neutral. It's 0. So I should basically have this structure. So for a neutral molecule, for a molecule with no charge, normally hydrogen has 1 bond, carbon has 4 bonds, nitrogen always have 3 bonds and a lone pair to be a 0 charge. Oxygen should have 2 bonds and 2 lone pairs to be a 0 charge. And if you have any halogens like a fluorine, a chlorine, like for example HF, this is the example that we explained at the beginning in there. Any halogen should have a single bond and the 3 lone pairs to again be a 0 charge. These are more examples drawing the Lewis structure. I'm showing both the bond line structure and the electron dot structure in there. So you start with basically getting the valence electrons. Once you get the valence electrons in there, you simply draw the molecule. We've drawn this in the slide before. We also drew this in the slide before. Now let's do the triple bond. For the triple bond, get the valence electrons. Valence electrons here is going to be 10 valence electrons. So we're going to distribute that. 2 carbons. Whenever you have carbons that are basically in a molecular formula, you always connect them together. So you have a carbon, single bond carbon as I'm having there, and then you have 2 hydrogens. Divide the number of hydrogens with respect to the number of carbons. So each carbon now is going to take 1 bond. Now I know that every carbon, to be neutral, it has to have 4 bonds, and this structure is neutral because it has 0 charge. So I want to make it 4 bonds. So let's see. I have 10 electrons so far. I've used 1, 2, 3, 4, 5, 6. Okay. So let's go ahead and fill out the rest of the 4. I have 7. I have 8. I have 9. And I have 10. So these are the 10 valence electrons in there. Now it does make sense if basically I combine these 2 electrons. 1 electron basically is very unstable. it's very unstable. It increases the energy of the structure. So this structure doesn't exist like this. These two electrons, since they are close to each other, will basically overlap with each other and make a bond. And these two electrons will overlap with each other and make a bond. So basically what I'm going to be having is a triple bond. So let me go ahead and draw it nicely. You're going to have a triple bond like this between the two carbons. So this way, this carbon has 4 bonds and this carbon has another 4 bonds. There is an exception to the octet rule, and the exception to the octet rule is basically in elements in the group 2A, like beryllium, like magnesium, like calcium. Those, they do have 2 electrons basically in their outermost shell. Their valence electron is 2. So beryllium has 2 electrons in its outermost shell. So it only makes bonds with only 2 groups. It doesn't make bonds with the 3 groups. Boron has 3 valence electrons in its outermost shell. This is 1, this is 2, and this is 3. So boron owns the 3 electrons and makes bonds with the 3 groups, so it shares 6 electrons. So there are basically 6 electrons around the boron. Another exception to the octet, so boron cannot make 8 electrons, beryllium cannot make 8 electrons, magnesium cannot, calcium cannot, they cannot make 8 electrons at all. Now, another exception to the octet rule, these are elements in the third row of the periodic table. Precisely, I'm talking about phosphorus and I'm talking about sulfur. And not just those, it's basically elements underneath or more than the third row. So if you go to the 4th row, 5th row, 6th row in the periodic table, all of these, they use D shells for bonding. And the D shell for bonding will enable these atoms to have more than 8 electrons, to exceed their octet limitation, so expand the octet rule. In that case, sulfur and phosphorus are the only inorganic atoms that we will be using in organic. Sulfur can make 10 electrons. This is an example where sulfur makes 12 electrons. Phosphorus can make 10 electrons in there. This is an example. Let's have an example. If I ask you to draw sulfuric acid, it's this one. This is sulfuric acid. So the first thing you would do, go ahead and get the number of valence electrons. It is 32. After you get the number of valence electrons, go ahead and figure out the unique element. It is sulfur. So sulfur is going to be in the center. The unique element is always in the center. Around the sulfur, there is the electronegative element, which is oxygen. Always leave the hydrogens till the end. See? Always leave the hydrogens till the end. So the way that I would do it, I would write the hydrogen, the oxygen, the sulfur, the oxygen here, the oxygen here, the oxygen here, and then another hydrogen. Now, of course, these hydrogens, you can link them to these oxygens instead of these oxygens. It's fine. So far out of 32, I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Let's continue to 32. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Notice I'm keeping in mind that every oxygen has to have 8 electrons. So this is why I have 3 lone pairs here. Here I have 2 lone pairs. Now when I am done in there, the way that this is written, oxygen is making 1 bond and the 3 lone pairs. So oxygen is going to have a negative 4 mole charge. Oxygen here will have a negative 4 mole charge. So the total charge for the compound is 2 negative, and I have it here as a 0. It's a neutral, but here it's 2 negative. This means that I should do something about these charges. I should get rid of them. So to get rid of these charges in there, normally oxygen should have 2 bonds and 2 lone pairs. to have a zero charge. So I need to make the oxygen having 2 bonds in 2 lone pairs. So you take out, not this oxygen, you take out one of these 2 lone pairs. So I'm taking out one of these 2 lone pairs here, taking out one of these 2 lone pairs there, and replace the lone pairs basically with a double bond. So I will have a double bond here, and I will have a double bond in there. Notice I didn't do that here. I didn't take the lone pairs on this oxygen because I would have oxygen with 3 bonds, 1, 2, and 3. And when oxygen has 3 bonds and a lone pair, its formal charge is a positive 1. There is a section of formal charges in this book that we will cover. Oh, here you go. So this is the formal charge in there. There are 2 ways to address formal charges, either by memorizing this table, you guys, or by simply working out the equation. The equation says it's just by calculation, but sometimes you don't have time to do calculation. You should know it on the spot. And by the end of this chapter and the end of all of your assignments, you should know this table by heart. So if you want to calculate the formal charges using this equation, you go by formal charge is equal to the number of valence electrons. So you look at the element, see what group number is that, minus all the unshared. The unshared are the lone pairs. Minus, the minus goes in there. So it's going to be minus half of the shared. Not plus, it's going to be minus half of the shared. The shared electrons, these are electrons that are shared between the element and the sigma bond. So we're going to start. If carbon is a 0 formal charge, carbon makes 4 bonds, nitrogen makes 3 bonds and a lone pair, oxygen makes 2 bonds and 2 lone pairs. This is in their most stable state. Sometimes carbon exists as a positive 1 charge, then it will have 3 bonds and positive a charge, plus 1. Or it can have a negative 1 charge where it should have 3 bonds and a lone pair. A positive in chemistry means that the element is losing electrons. A negative in chemistry means that it is gaining electrons. So let's take a look here. You can use this formal charge formula to calculate that plus 1. So I can do that. Carbon has valence electron 4 minus how many unshared do I have? None. I don't have any lone pairs, so it's going to be minus 0 minus half of the shared. The shared is 1, 2, 3, 4, 5, 6. So basically it's going to be 6 divided by 2, so it's going to be 3. 4 minus a 3, that is going to be equal to plus 1. So instead of wasting time doing this formula over here, I already know that when carbon has 3 bonds and a plus 1 and 3 bonds, its formal charge is going to be positive 1. Okay. Oxygen and sulfur, they are basically in the same group. So if they are in the same group, they normally follow the same formal charges. Although sulfur expands the octet rule, sulfur can use its D shell in order to occupy more electrons in its outermost shell. But in case sulfur has the same bonds as oxygen, then sulfur is going to have the same formal charge as oxygen. So if sulfur, you can add also this to the formal charge table. So if sulfur has 3 bonds and 2 lone pairs, its charge is positive. If sulfur has 2 bonds and 2 lone pairs, its charge is 0. And if sulfur has 1 bond and 3 lone pairs, its charge is negative 1. This is an example over here. This is an example where I am asking to calculate the formal charges of sulfur and oxygen. So calculate the formal charges of sulfur and oxygen in there. You need to figure out. And once you figure out the formal charges, you have to include this in the formula of the Lewis structure, as I am doing over here. So to calculate the formal charge of the sulfur has 3 bonds and a lone pair. Let me go back. When sulfur has 3 bonds and a lone pair, you should get an answer of plus 1. formal charge, apply this rule. So the number of valence electrons of the sulfur, I know that sulfur is 6, minus in this case half of the shared, see how many shared I have, 1 2 3 4 5 6 for the sulfur, so it's going to be 6 divided by 2, so 6 times half, minus the unshared. The unshared is the lone pair on the sulfur, and that is 2. This is going to be equal to positive 1, so you can easily figure that out. You do the same thing for the oxygen. Once you figure out your charges, you just include it in the formula, in the Lewis structure in there. This is another example. Calculate the formal charges for the atoms in nitroethane. I'm giving you the nitroethane structure there, and I'm asking you to calculate the formal charges of oxygen 1 and oxygen 2. So I know from the table that when nitrogen has 4 bonds, then its charge is positive 1. When oxygen has 1 bond, its charge is negative 1. So the formal charges there are positive for the nitrogen, negative for the oxygen. This means that the total molecule is a neutral. It is a 0 charge. Now, in case I did not give you the Lewis structure, you have to draw it. And in order to draw it, you would need the molecular formula. This is the molecular formula. It's telling me that the 2 carbons are connected together and they are connected to the nitrogen. So I'm having a carbon-carbon nitrogen in there. And then the oxygens are connected to the nitrogen. And see those hydrogens? They belong to the carbon. So hydrogens belong to the carbon in this case. You distribute them along the carbon. So the first thing, calculate your valence electrons. After you do this, just go ahead and do the connectivity. And count the electrons around the electrons that you use. This is 1 2 3 4 5 6 7 8 9 10 5 6 7 8 9 10 11 12 13 14 15 16. Let me go ahead and draw it in there just to show you. So you have your carbon, and then you have your nitrogen, and then on the nitrogen I have these 2 oxygens there, and then on the carbons I have my hydrogen. So far this is it. Now I need to make sure to distribute all my 30 electrons, 30 valence electrons in this structure. So I'm having 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 and 30. See, so I am done here. But I am done. Everything is octet, yes, except what? Except the nitrogen. The nitrogen is not octet because the nitrogen has only 6 electrons. It should have 8. Nitrogen should have 3 bonds and a lone pair, so it should have 8 in this case. So what I would do over here, let me make sure that I did that right. Probably I missed 2 electrons there. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 and 30. Let me go ahead and double check this and make sure that our valence electrons are right. So I have a 12 there, plus 10, this is 22, 22 plus 8 is equal to 30. So yes, I do have 30 valence electrons in there. So we should be fine. We should be good. We have 30 electrons. So now what I would do easily, because I need now this nitrogen, this is not octet. I needed to have 8 electrons. So you can easily take 2 electrons from the oxygen. Okay, either this oxygen or that oxygen, it doesn't matter, and go ahead and put a double bond in there. Now this way, what do I have? This way I would have a positive charge on the nitrogen, because nitrogen is going to have 4 bonds, and a negative charge on the oxygen because nitrogen has 1 bond. You can easily apply the formal charge formula in order to calculate this positive and negative charges if you don't want to use the table in there. Now this is going to be my Lewis structure. After you do your Lewis structure, make sure it includes all the lone pairs and the charges. This is another example in there. So draw the Lewis structure, show the atoms. This is just an extra practice. So NH2, we're going to do a couple of those. So with the NH2 negative, okay, now when you have a negative charge, what does that mean? Negative charge means it's the charge of the whole molecule. So when you draw your Lewis structure, you want to figure out where your negative charge is on that molecule. This negative charge means that I am gaining 1 electron. So you should, when you are counting the number of the total valence electrons, you should go ahead and include this in the valence electrons. So negative 1 means I am adding 1 electron. Negative 2 means I am adding 2 electrons in the valence electron. A negative 1, again, I am adding 1 electron. A positive 1 means I'm losing, and I am losing 1 electron. So you have to subtract 1 electron in the from the valence electrons. Make sure that you do this, or else your valence electrons is going to be odd. We cannot have odd valence electrons. As you can see in all of these examples, the valence electrons is always even. So you start with calculating your valence electrons, and then you have nitrogen, you have the 2 hydrogens in there. Go ahead and add the extra electrons. So I have 1, 2, 3, 4. I need 4 more. So add them on the nitrogen, and then calculate your formal charge. I know that nitrogen having 2 bonds, 2 lone pairs, it should have a negative charge. Another example is basically the bicarbonate ion, the HCO3. As I said in there, calculate your valence electrons and then draw the connectivity. So what I have here is carbon is the unique element. Carbon is the unique element, and this carbon is connected to 3 oxygens. So draw your 3 oxygens in there. Don't put the hydrogen on the carbon. Carbons, we can fill their octet by doing double bonds with the oxygen. The hydrogen has to be on one of these oxygens in there, any one of these oxygens. So go ahead and put the hydrogen there. And then fill your 24 valence electrons. So far I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. I am done over there, but carbon is not octet. This is an easy fix. Take 2 carbons out from the single bond oxygen, not from the 2 bonds, from the single bond, and simply draw a double bond between the carbon and the oxygen. So you can take electrons either from this oxygen or from that oxygen, whatever you want. So in that case, you will be left with an oxygen with a single bond there. That is going to be a negative charge. That negative charge is going to reflect the negative charge, the total charge of the atom, of the molecule that you are having in there. CO3, 2 negative, same thing. Draw the carbon with the 3 oxygen bonds. I have 24 valence electrons. Just go ahead and fill them. I have 6 so far. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Carbon is not octet. Again, this is an easy fix. Take these 2 electrons out and make a double bond between the carbon and the oxygen. So in that case, I would be left over with a negative charge on this oxygen and a negative formal charge on the other oxygen. And that is going to be my Lewis structure in there. The carbonic, basically over here, the acetate ion, the CH3COO negative. Do the same thing. I have the CH3, the C, the 2 O's. So as it's written, connect it. CH3 means I have a carbon with the 3 hydrogens. See how my carbons are connected with each other? And then you have the 2 O's are connected to this carbon. So you have the 2 O's in there. Then count your valence electrons. Make sure you distribute all the valence electrons. And then take 2 electrons from the oxygen, as we did in this example over here. Take 2 electrons from the oxygen and draw a double bond for the carbon to be octet. And in that case, you will be left with 1 negative charge. That negative charge is on the oxygen. So my point is, if you have a structure with a negative charge, you don't know where the negative charge is. It is not necessary on the center atom. So you have to figure it out. To figure it out, you have to draw the Lewis structure. These are more examples that you can practice. They go with the same rule there. In this example in here, in this example, it shouldn't have anything there. You should fill it out. So let me go ahead and erase all of those out. So you should fill those out. So it says fill in the bonds. You have HCN. Cyanic acid, the first thing, calculate your valence electrons. This is 10 electrons over there. After you calculate your valence electrons, just go ahead and draw the connectivity there. Here you go. So I have hydrogen, carbon, nitrogen. This is what I have. Fill out your electrons. So to fill out my electrons, I have 1, 2, I have 3, 4. I have 5, 6, so 1, 2, 3, 4, 5, 6. I do have 7, 8, and I do have 9 and 10. Okay, now the nitrogen is octet, yes, but carbon is not. So in this case, what I would do, this is an easy fix. Every time carbon is not octet, carbon can make double bonds and triple bonds with nitrogen. Carbon can make double bonds with oxygens. Remember this. So I'm going to take 2 electrons in here. Remember, every 2 electrons make a double bond. So a bond, I'm sorry. So I'm going to make a bond here. And then I'm going to take 2 electrons from this nitrogen again. And I'm going to make another bond in here. So now my nitrogen has 3 bonds and the lone pair, it's 0 charge. Carbon has 4 bonds, it is 0 charge. So the connectivity has to be a hydrogen single bond carbon and a triple bond nitrogen. Here we did this example before. The connectivity is going to be single bond and a double bond with the oxygen. Please refer to the slide before for the form aldehyde, or for the aldehyde example that we did. Another example is this structure. As you are seeing it, just to draw it, but first calculate the valence electrons though. You have 30 valence electrons, and then as you see it, you draw it in there. So you have hydrogen, oxygen, carbon. So let's go ahead and draw single bonds for each one of those. Okay, so far I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 out of 30. Let's go ahead and continue. 17, 18, 19, and 20. I'm done with this oxygen. It's octet. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So now counting those, they are 30 valence electrons. I'm done, but carbon is not octet. Carbon has 6 electrons. It has 3 bonds only. So what you need to do over here is simply, this is again an easy fix. All what you need to do, look for the carbon single bond oxygen, erase 2 electrons from the carbon single bond oxygen and make a double bond. And that will be the structure in there. You make a double bond in there. If you have a carbon double bond OH, this is another functional group which we're going to call carboxylic acid. All of these functional groups, these are groups that carbons make with electronegative elements. These functional groups we will discuss in chapter 3.